Welcome students to this video module. In this module we are going to learn about different configurations of transistors. In the last module we learned about the two types of bipolar junction transistor, that is NPN transistor and PNP transistor. Okay, we know that there are three regions in a transistor, so we have three terminals also, but we know that a transistor is a device which needs an input and an output. So it needs two terminals for input connection and two terminals for output connection. So totally we need four connections. How is it possible? Because transistor has got only three terminals. So the solution is to use one common terminal, or one terminal as a common for both input and output. So that is actually that is the need for using various configurations in a transistor. Okay. So we have three different configurations for a transistor. We can check which are the three different configurations. The first one is common base configuration, second one is common emitter configuration, and the third one is common collector configuration. Okay. Let us see what is meant by common base configuration. Okay, in common base configuration, the base of the transistor, you know that base is the lightly doped and thin region in a transistor. So in a common base configuration, we use the base region of the transistor common to both input section and output section, as shown in this picture. You can see this is an NPN transistor. We learned about NPN transistor and PNP transistor in the last module. So this is we are explaining this on the basis of NPN transistor. Similarly, you can write for PNP transistor also. Only thing is that you have to change the direction of current and reverse the direction of battery is also. Okay, so this is an NPN transistor shown here in its common base configuration. In common base configuration, you can see that base of the transistor is connected common to the input section and to the output section. Okay, so now we already learned transistor is a device used for getting and transferring signals from a low resistance region to high resistance region. In order to achieve that, we made the input section as forward biased and the output section the reverse bias condition. So when we transfer signals from low resistance region to high resistance region, there will be some sort of change in the signal, or we call it as amplification. There will be some sort of amplification. Okay, because the basic one of the basic application of a transistor is also for amplification purpose. Okay, so we can express the term amplification, or better known as current amplification factor, for a common base common base transistor configuration. Alpha, what is alpha? Alpha is the current amplification factor. That means how much the output compared to the input voltage. That is, in this common base configuration, we know that the output voltage is IC. IC is collector current, and the input current is IE, that is the emitter current. So the ratio of output current to input current is known as amplification factor. That is, whatever be the configuration, the definition of current amplification factor is output current, the ratio of output current to input current. In this particular case, that is in common base configuration, output current is IC, the collector current, and input current is IE, the emitter current. So the current amplification factor is IC divided by IE. Okay, this is the expression for current amplification factor in common base configuration. And practically the values of this current amplification factor in common base configuration is in the range 0.9 to 0.99, because we know that IC is almost equal to IE. We learned an equation, I think we learned the last class the equation that IC is equal to, IE is equal to IB plus IC. this IB is very less because the base region is lightly topped. So IE is almost equal to IC. Therefore, IC divided by IE will give a value almost close to 0.99 to 0.9 to 0.99 volt. Okay, this is the range of current amplification factor in case of a common base configuration of NNP and transistor. As a note, you can refer that in the collector region, other than the current reaching from emitter to collector, there is another current also that produced due to the reverse bias, because we know that the output circuit is reverse biased. So in reverse bias there will be a small current. We already learned in the case of diodes and all. Because of the applied reverse bias, there will be a current due to minority carriers. In this case we call it as ICBO. That is the current. ICBO is actually the collector base current in the when the emitter is open. It's a collector base current when the emitter is open. That is the reverse. Actually, it is the reverse current due to minority carriers in the collector base region. That is a very small value. So the actual collector, we know that collector current, the current from emitter, the charges from emitter region move towards the collector through base region. As the base region is slightly doped, most of the charge carriers move to collector. That constitutes a collector current. So other than this collector current, there will be a small current due to the presence of the flow of minority carriers also. We represent that by this ICBO. So what is ICBO? It is the collector current. It's a collector base current when the emitter is open. ICBO is the collector base current when emitter is open. So in real practice, we can say collector current IC is actually equal to the collector current originating from emitter, along with that the current due to minority carriers present in the collector. So okay, just keep in mind that note also. Okay, so from now from this common base configuration, now we are moving to the next type of configuration, that is common emitter configuration. So from the name itself, I think it's from the name itself, it is very clear that in this type of configuration, the emitter of the transistor will be common to both input circuit and the output circuit. You can see that emitter is connected common to the input circuit. This is the input section. And this is the output section. So it is common to the input section and output section. The emitter is common here. So that is why this is known as common emitter configuration. Okay. So in this case also we can learn the current amplification factor. What we learned current amplification factor in the last type of configuration, it is the ratio of output current to input current. Here also the same. The current amplification factor is always the ratio of output current to input current. So here the output current is IC, the collector current, and the input current is base current. So the ratio, current amplification factor. Here we represent current amplification factor with the letter beta. In the previous case it was alpha. So here the current amplification factor in case of common emitter configuration is IC divided by IB. That's output current divided by input current, IC divided by IB. Okay. Now we are and one more thing here also, the collector current is actually a combination of the current that originating from emitter along with the current due to minority carriers present in the collector. As in the previous case, the total collector current will be the current originating from emitter plus the current due to minority carriers present in the collector region. Okay. Now we learned what is meant by common emitter configuration and its current amplification factor. I told that current amplification factor current amplification factor tells how much the input current is changed when it reaches the output circuit, or it is the ratio of output current to input current. So beta is equal to IC divided by IB. Now we have to find a relation between alpha and beta. What is alpha? Alpha is the current amplification factor in common base configuration, and beta is the current amplification factor in the common emitter configuration. So in order to derive a relation, you consider the current equation in case of a transistor, that is IE equal to IB plus IC. emitter current. We learned in the previous session. I is equal to IB plus IC. Now you divide both sides of this equation with IC, so you will get a relation like this. Okay, now these all things are familiar. What is IC by IE? This one. This is actually you learned IC by IE as equal to alpha, so this is actually 1 by alpha. And what is IB by IC? We know IC by IB is beta, so IB by IC is 1 by beta, and IC by IC is 1. Now on simplifying this, we'll get beta equal to 1 alpha divided by 1 minus alpha. So this is the relation connecting current amplification factor in common base configuration and common emitter configuration. Okay, students, so from this we are now moving to the third type of transistor configuration, that is known as common collector configuration. What is common collector configuration? In this type of configuration, collector of the transistor will be connected common to the input section and output section. What is that? In this type of combination, the collector terminal will be common to input section of the circuit and output section of the circuit. Okay, and in this type of combination, the current amplification factor. What is current amplification factor? It is a ratio of output current to input current. Here you can see output current is emitter current IE, and input current is the base current IB. Now the ratio of output current to input current is known as current amplification factor. Here it is represented by gamma. So gamma is equal to IE divided by IB. Okay, now we have to find the relation connecting all the three current amplification factors. So for that, we are again taking the equation connecting different currents in a transistor, that is IE is equal to IB plus IC. Now you divide both sides of this equation with IB. So IE divided by IB is equal to IB divided by IB plus IC by IB. Okay, this will give, what is IE by IB that we just now learned? It is gamma. What is IC by IB that we learned in the previous case? That is beta, and IB by is 1. So gamma equal to 1 plus beta. That is the relation connecting gamma and beta. But we already know that beta is 1 alpha by 1 minus alpha. Substitute this in this equation. We will get gamma is equal to 1 plus alpha divided by 1 minus alpha. Then solving for this, we get gamma, the current amplification factor in common collectors configuration, is equal to 1 by 1 minus alpha. Gamma equal to 1 divided by 1 minus alpha. Okay, students, so this is about the transistor configurations and the respective current amplification factors in 3 cases. Okay, students, thank you.